Okay guys, let's take a look at today's lesson. So what we're going to be looking at is a brand new coordinate system. We've really worked with the Cartesian coordinate system for years and years. We are very familiar with it. It has the x-axis, the y-axis. We know what signs everything is, where x is positive, where x is negative, and so forth. But there are other coordinate systems out there that are good for different kinds of things. One of those is polar coordinates. It's a completely different coordinate system. We measure things differently. We don't look at them as in the first and second and third and fourth quadrant. They're different. So let's talk about that. We're going to learn how to use this system today to convert back and forth between rectangular, which is Cartesian, and polar. So first let's look at how it's created. How would we write a point in polar form? The points are written with r and theta. So r, I like to think of it as rings. Really, I guess technically it's radius. It's the distance from the origin or pole that the point is. So this distance right here is r. The theta, or angle measure, that's the angle measure, and at this point you're going to be super excited that you've had to remember all that trig this time, because this is all about trig, about unit circle values, about trig formulas. This unit is all about trig, and it's basically the polar grid like a unit circle. It's got the same measurements in radians as a unit circle does. It's exactly the same. So this measurement, this theta measurement, is actually an angle measurement, and it's measured from the, here's the pole. It's measured from this, we would consider it an x-axis in the old system, and rotates. Just like if we're rotating this way, it would be a positive angle. If we rotate backwards, it would be a negative angle, just like our unit circle. Okay, so that's going to be very familiar to us. In order to be able to switch back and forth between those two types of coordinate systems, the polar coordinate system and the Cartesian coordinate system, we have to have a way to do that, and so we do. We have formulas. There are 4 formulas that you'll have to memorize. Okay, these are our 4 formulas. We actually, if you are going to be taking Calculus 2 at some point, which is part of the BC curriculum, we have polar, we find the area of polar curves in there. We do all kinds of things with polar. So these things, these formulas, we have to memorize for this unit, but also you'll need to know them next year if you're going to be in BC calculus. We work with polar. Okay. So what is happening here is I have a relationship between x, r, and theta. That's what these formulas provide for us, is a relationship between the 3 variables, because we are going to be able to need to go back and forth from one system to another. Okay, so any questions so far? All right, let's go ahead and go to the examples. Okay. So here is a picture of a polar grid. On Moodle, I do have some blank polar grids if you want to print them out, if you need them for something. The polar grids that, I'll give you the polar grids that you need for the daily work and such, but if you need extra practice, you can certainly print those off. So let's work on how do we plot a point in polar form. So let's start with this is the easiest one. So this would be our r, and this is our theta. Okay, so I'm going to r. I like to think of them as rings. So we see these rings as they move out. This would be a ring of 1, right? This is 1 unit from the pole from the origin. That's 2 units, and so forth. So we would go to the first ring, and then we would know at 3 pi over 4. So we'd go to 3 pi over 4. Right here, and we would go to the first ring, and that would be our point. That's our A point. Okay, so we are at 3 pi over 4. Alright, so let's do this a little bit different. We have a negative rotation on this angle on part B, so I need to go to negative pi over 6, and so we are familiar here. Negative pi over 6 would be the same as 11 pi over 6, so it would be down here, and I want to go to the third ring. Okay, so we go 1, 2, 3, and this would be our location for B. Okay. C, 3 pi, well we know how to do that, right? That's just more than one rotation, right? 3 pi, we would go around to 2 pi and then around another pi would put us here, and we would need to be on a ring of 5. So 1, 2, 3, 4, 5 would put us right back out here. Now the strangest one, the one that students have the most trouble with, is like D. So let me kind of talk about this. When we are in the Cartesian coordinate plane in x and y coordinates, we know where x is negative, right? We know there's no doubt x is negative in the second and third quadrant, right? We know where y is negative, right? It's in the bottom, the third and the fourth quadrant. R can be negative anywhere on here, anywhere. So it's kind of confusing to students, like how do I know? Well, let's kind of walk through it kind of slowly. So how do I know how to plot a negative r? Well, what I would do is I would go to this angle measure, whatever angle measure is indicated. In this case, it's pi over 4. So I'd go over here. Now, this is where, in this location where pi over 4 is, which is from the origin out, that's pi over 4. These are all positive r's over here. If I want a negative r, what I have to do is it basically shoots me to the other side of the grid. It puts in a, we'll talk about it as quadrants. This is the first quadrant. It would shoot us across to the third quadrant. That's where our point would be. That's how a negative r affects the point. So wherever the angle measure is, you would go to the opposite side and plot the point. So we are at pi over 4, so we would need to go to 5 pi over 4 and go to the fourth ring. And this is where point D would be. Okay, are we okay on that? So that's just a little bit of a nuance. I think once you'll get used to that, it'll be just fine. So as with angle measures in our unit circle, there's an infinite number of ways we can write each point. That's not so in the Cartesian coordinate system, right? If I have a point at 1, 1, I know exactly where that is. It's 1, 1, and there's no other way to say that. I guess you could say 2 over 2, comma 2 over 2, but that's still 1, 1, right? I mean, same spot. But for each of these locations, I could come up with an infinite number of ways to write them. And so we're going to practice that. We're going to practice that with this problem right here. So let's just see, where would pi over 3, 2 be? Let's just kind of plot that over here. So let's go to pi over 3 and go to 2. So right here, that's what we're looking at for, this is number 2. Okay, so that's the location that we are interested in. And what they're asking us to do is to find 2 different polar representations where r is positive and 2 other ones where r is negative. Of course, there's an infinite number. We're just picking 2 of them. So let's think about how we would do that. Let's do it with r is positive. So that means I need, 2 positive ones. I just need to come up with the angle measure. So let's think about what would we do. I mean, so this is where I am. Could I put another rotation on it? Sure. Sure, I could add 2 pi to that, right? And that would give me the same exact location. Could I go backwards? Could I go this way? Sure, I could put a negative rotation on it, right? I could go this way and get that angle measure, and that's actually what I did for these. So the first one, I added another rotation to it. I added 2 pi, so that gave me 7 pi over 3. And the other point, I decided to do a negative rotation, so that gives me negative 5 pi over 3. Okay, so that's when r is positive. Now let's look at what happens when r is negative. Now they want us to do some points where r is negative. Okay, so we're going to have r negative, so we're going to have to come up with the proper angle measure. So r is negative. Let's think about that for a second. If I am here and I want my r to be negative, where would my angle be? It would be down here, right? Wouldn't it be in the third quadrant? So I just need to follow this down and see, or I mean, I guess you could just add pi to it because they're just pi spaces apart. And that would put me at 4 pi over 3. Okay, so that's what's going to give me that location, negative 2, 4 pi over 3. And then with a negative rotation, it would be at negative. So we're looking down here, right? For a negative r, our angle measure needs to be down here. And so to get down here, negative would be negative 2 pi over 3. Okay? Now there's a lot of other ones that you could do. Certainly it's your choice which ones you write. I just like a 1 positive rotation and 1 negative rotation is pretty good. All right, on the next two, we're going to learn how to go back and forth between rectangular form and polar form and coordinates. We're going to be in coordinates. Now, I want you to understand that this is actually very precise. I am looking for a particular location. So, for example, here, this is 4 2 pi over 3. So let's plot that, see where that would be. So 2 pi over 3 went here, and then 4. So this is number 3. Okay, that's the location I'm looking for. I want that exact location, but I want it to be in Cartesian form. So in other words, if I were to overlay this, polar grid with our Cartesian grid, I should be able to plot this exact point with what I'm coming up with over here. Okay, so there it's an exact location for location. So let's look at, we have 4 formulas that we need to memorize for use for translating back and forth. So we have x equals r cosine theta, y equals r sine theta. Now these two should not be that difficult to memorize, right? Because we know x normally goes with cosine anyway, right? And y normally goes with sine. So that should be kind of a, oh yeah, that makes sense. All right, and then the other two are x squared plus y squared equals r squared. And I don't think that one's too bad to memorize. And then we have tangent theta equals y over x. And this tangent theta one should make sense, right? Isn't it normally y over x, sine over cosine? So those should be, not too difficult to memorize. Okay, so we are going to use these formulas to be able to take our points from, polar to rectangular or back. So I have a polar, so this is my r and this is my theta. I have a polar point, and I need to turn it into an x and a y. So I look at those equations and try to decide what would be my best bet. Well, I have an r and theta, and these have r's and thetas. Wouldn't it be better to use these two equations? Now let's use these two equations to translate. So I have x equals r, which is 4 cosine of 2 pi over 3. And we know, 2 pi over 3 is right here. What's cosine at this location? Is it positive or negative? It's negative, right? Cosine? Negative what? 1/2. Negative 1/2. Our unit circle values should be right in our head, right? Because we've been having to use them on every single quiz and test, okay? Right there. They should be right on the tip of our tongue. So this is going to be 4 times negative 1/2, which is negative 2. So y is going to be, it's r sine theta, so it's going to be 4 times sine of 2 pi over 3, or 4 times, and what would sine be at 2 pi over 3? Root 3 over 2, right? It would be root 3 over 2. So y is 2 root 3. So this point, if I were to overlay a Cartesian coordinate grid here, this would be at negative 2, positive 2 root 3. And that's where we would be, right? That would be the exact location. So negative 2, 2 root 3. Is that okay? Okay. So now let's go the other way. This is x and this is y. So let's go and let's turn that into a polar coordinate grid. All right. So let's see, x and y. This really wouldn't help us that much if I had that x and that y. How do we know what r and theta would be, right? Wouldn't these be better to use if we had the x and the y? So let's put the x and the y in these two equations. So we would have 2 squared plus negative 2 squared equals r squared, or 8 is r squared. Our r is plus or minus 2 root 2. It could be either one, right? I have an infinite number of ways to write that point. So I could use a positive or negative r. Okay, so let's just leave that there. I don't really know where we're going with that yet. Let's find the other one. So tangent theta. So tangent theta equals y, which is negative 2, over x, which is 2. So we need to think about all the locations where tangent is negative 1. Where is tangent negative 1? 3 pi over 4, right? So theta could be 3 pi over 4. It could be 7 pi over 4. I mean, we got lots of options, right? Now here is where we have no option. Okay, whatever point we come up with has to be in the exact same location as this point, or we haven't done our job. Right? What quadrant is this point in? 2, negative 2. It's in the fourth quadrant, right? This is in the fourth quadrant. So we have to pick a combo of these, these numbers down here that will put us in the fourth quadrant, because that's what we're looking for. So I came up with 2 different options. Of course, there's an infinite number of that location. So I came up with 2 root 2 negative pi over 4. Okay, that allows me to use a positive r, or one case where it allows me to, or negative 2 root 2 3 pi over 4. Those are 2 options of, a lot of different options, but both of those options will put us, to negative 2. They should put us in here. Okay? All right. So that is how we graph in polar coordinate form. That's how we, have different representations of the points and take the points back and forth. This is the most basic part of it. It gets a little bit more tricky when we are trying to take an entire equation from one form to another rather than just a point. And that's what we're going to be working on 5 and 6. We're going to take an entire equation from one system to another. And when we do that, we're going to be using these 4 formulas. And there's no cut and dry thing to do. I mean, we'll use all 4 of them at different times. For transforming points, that's pretty straightforward, right? You use, if you're going from rectangular, going to rectangular from polar, you're going to use these, right? And if you're doing the other, you're going to use those. That's pretty straightforward, but not on these problems. All right, so let's take a look at number 5. To go from Cartesian to polar is actually probably the easier one, in that we know what x and y is. We have that right here. Why don't we just plug that in? That's the easiest step. Let's just plug this in for x and y. So this x squared becomes r, so r cosine squared that I'm substituting. I'm substituting this formula in for x. And then 4 times r sine theta. Okay, so that's the easy part of this type. The harder part is to get it to look right. Okay, this is what polar equations look like, right? Not like this. Like this. So we need to figure out how to make it r equal something. So the first thing would be, let's just go ahead and square this side. So I have r squared cosine squared equals 4r sine theta. Now, something that I'm getting ready to do will probably trouble some of us. And I want you to know when we're converting these, it is okay to divide off an r or to multiply both sides by an r. That is okay. I know that's not okay in rectangular form because we lose stuff, right? We lose like solutions and all that. But in polar form, it's okay. So I'm going to divide off an r, and that's going to leave me with r cosine squared equals sine. And then I want to solve for r at the same time. Okay, so I'm going to do 2 steps in one. I'm going to divide the r off, and I'm going to move the cosine squared over. So I'm going to get r equals 4 sine theta over cosine squared theta. Okay, so I've accomplished my first goal, which is to get r equal to something. Now, we normally don't see polar equations in fraction form. Okay, that they normally look like this. So if we can get it out of fraction form, we need to. So this is where our trig identities come in. So we look at that. We know sine over cosine is tangent. And 1 over cosine is secant. So can't we turn sine over cosine squared to tangent times secant? Right? Are we comfortable with that? That's how we would write this problem. We would say r equals 4 tangent secant. Okay, and so that's going from rectangular to polar. Okay, we all okay with that? All right. So let's go on to the other ones, a little bit more challenging, going from polar to rectangular. Now I really need you to be listening because every year I have students do this. Every year. Let's go for this year for no one to do this, okay? When I am transforming out of polar form, I am not allowed to have any trig left at all. None. Some students will like change this to like secant x or something. Like, oh, I got an x. No. You can't have any trig left at all. It has to be completely eliminated. Okay, I just want to make that perfectly clear. The only thing that you're allowed to have in there are x's and y's. Some configuration of x's and y's, no trig. Okay? Hopefully I'm making that so. No trig left. Okay, yes. Sine, cosine, that's right. No sine, cosine, tangent, secant, cotangent, none of that. None of those sine functions left. Only a simple x, y, or x squared, y squared, something like that can be left. So I just wanted to make that really clear because every year I have someone trying to transform these and leaving trig in there. Okay, we don't do that. Okay, so let's look at this. I don't really have any secants up here. Let's think, well, I can turn secant into some different stuff. That's where our identities come into play. I can turn secant into 1 over cosine, can't I? And that at least will get me a cosine. So let's do that. Let's turn secant into 1 over cosine. Okay, so that's good. That makes me happier. So I got a cosine. I really want an r cosine. So couldn't I just multiply both sides by cosine? If that's okay. And I would get r cosine equals 5. And we know r cosine is x. So let's talk about this. This is kind of a strange polar graph. Most polar graphs are all curves. This polar graph, 5 secant, is x equals 5. And they match each other perfectly. Right? If I graph x equals 5 in Cartesian coordinate form, you know what that looks like, right? You'd go over to 5, and once you put a straight line here, that's what it's going to look like in polar form too. It's going to be weird. I mean, we don't normally see straight lines graphed. That's what would happen. If you graph 5 secant in polar form, you would get x equals 5. Okay? So they are they are perfectly matching graphs from one coordinate system to the other. Just like I was explaining here, they're perfectly matching points from one system to the other. Right? They match exactly the exact same location, so their graphs should too. No, it's just going to be like a slash like that. Yeah, I mean, it'd just be weird. I mean, that's weird, right? Yes, exactly the same. Just strange looking. Okay. So on this one, let's look at our last one. I could square both sides, and that would help me out here with the r squared, but would that help me over here at all? No, that wouldn't help me at all. So now I'm going to use a technique that is fairly common, which is not common in Cartesian form. I'm going to multiply the entire equation through by an r. Both sides, everything is going to be multiplied by an r. So I would get r squared equals 2r plus 2r cosine theta. Okay? At this point, what I like to do is I like to go ahead and transform the things I can transform. It's kind of like, oh great, you know, let's get rid of this. We want to get rid of things we can get rid of and turn them into x's and y's. So I have an r squared. I'm going to go ahead and turn it into x squared plus y squared, just for my peace of mind, and also to see what I have left over. What do I have left over to work with? Is there anything that I can do to the 2r? I don't have any formula up here that will handle a 2r, do I? I might be able to, so let's see let's just leave it behind for now. Let's leave it behind and see what we're going to do. What about this 2r cosine? Do I have something for that? I do, don't I? What is r cosine? X, so this would be 2x. Okay, so we're doing pretty good. We've eliminated everything except for the r, 2r. Of course, we can't leave it, so let's see. Why don't we pull the x's and the y's together, get them on the same side, and kind of, you know, divide and conquer, right? Just move them over and then let r be by itself. So 2r equals x squared plus y squared minus 2x. Okay. So let's think about what can we do? What can we do to get rid of that r? Would this be now a good time to square both sides? Would that work for us? It would be a huge mess, but would it allow us to get rid of our last little r? Yeah. Yeah. Woohoo! All right, yay! Okay, let's do that. Let's square both sides. 4r squared equals x squared plus y squared minus 2x squared. Now don't go crazy and start foiling that yet. Just hold on. Hold on. Okay. So I'm going to replace the r squared with x squared plus y squared. So 4 times x squared plus y squared equals x squared plus y squared minus 2x squared. Okay. So that's just a lovely, lovely. Now, maybe you can see, which do you think, I know you don't know how to graph polar yet, but if you just think about it, do you think it would be easier to graph this or this? I'm thinking this, right? This, I mean, what is that? What is it, right? I mean, if I squared this, let's just think, I don't want you to square, but I want you to think about it. If I squared this, wouldn't I have like an x to the fourth and a y to the fourth? Okay, and I have an x squared and a y squared over there, and all other kinds of x squares and y. I mean, it would just be this massive mess, right? So in situations like this, where you have this big, massive thing, we just leave it alone. We're like, oh, you're so nice. Let's just leave you alone. We're just going to leave you alone, just like that, because if I try to do anything with you, I'm not going to turn you into something that we know. Is that going to look like an ellipse or a parabola or a circle? Or no, I mean, that's crazy, right? That's going to be crazy. So there's no sense in trying to make it look better. That's as good as it's going to look, right? That's as good as it's going to look. And so we just leave that alone. And I know that's not the norm. Normally we're going to change the equation to look like what it's supposed to. Like if you get a line, you need to make it look like a line. You know, if you get a parabola, you need to make it look like a parabola. But this is not either of those. Okay. All right. So questions.